Okay, greetings aspiring scientists. Welcome to my lecture today on metallic bonding. You might notice I'm in a different place than usual in the rest of my videos. I'm not at home, I'm at school today, but all classes have been canceled due to bad weather, so I've got nothing to do. I figured I would try to make a video. This is not really the optimal or ideal production setting I would like with the mic and the camera and all this, but I'll just do my best. So let's go to my slides. We're now at 2.3.1 in the IB Chemistry SL curriculum, metallic structures. So I want to remind you, we've talked about a lot of different types of chemical bonding. Ionic bonding, this is a lattice between positive and negative ions, such as NaCl. We've talked about covalent bonding in the molecular type, which is something like water, which is held together, individual molecules held together by intermolecular forces, such as hydrogen bonding in water, but also dipole-dipole, London. Then there's covalent bonding networks, such as diamond or graphite or silicon dioxide. These are a series, a lattice of covalently bonded atoms, non-metal atoms in all directions. It could include metalloids as well. So the last one that we have not done yet is the bottom left here. This is metallic bonding. So you can kind of see it's similar to others, but also different. It also has a lattice. It has cations, and it has electrons, but they are not locked in place in specific bonds, such as in a covalent network. But we will get into that today. So let's take a look at this table, metallic bonding in pure elements. So you can see we're going across the periodic table from left to right. We're in period 3, it looks like, going from sodium to argon, just straight across the periodic table and looking at some properties. So how do we classify these? We classify sodium, magnesium, and aluminum, Na, Mg, and Al, as metals. Then when we get to silicon, Si, we'll say that's a metalloid. It contains properties of both metals and non-metals. It's hard to define. But then from phosphorus, sulfur, chlorine, and argon, we go into the non-metal territory. So they have much less metallic properties, more non-metal properties. So what's the structure here? So of the ones we've talked about, from phosphorus to argon, these have molecular covalent structures, so they will form maybe like
diatomic molecules,
or groups of 6 or groups of 8 atoms bonded together covalently, and then they will be held together with intermolecular forces. Argon is not really molecular covalent even, it's just atomic, right? It's just argon atoms as a noble gas. So I probably should have changed that, but just keep that in mind. Then silicon is a covalent network instead. It doesn't form molecules, but probably due to the fact that it's in between metallic and covalent molecular, it's sort of on the edge. It's still forming a crystal lattice, but instead of having free electrons, those electrons are locked in place as they get more and more covalent. So what are some properties of these? We have electrical conductivity we can consider. Very high for sodium, magnesium, and aluminum. I think most highest for aluminum. Then we get to silicon. It's known as a semiconductor, which is just what it sounds like. It's semi-good or slightly good at conducting in certain situations. But it sort of needs specific situations or certain kicks of energy through light or heat to actually be a good conductor. Sorry if I'm tripping over my words a little bit. It's really cold in here and I'm trying to get my face muscles to move. Anyway, so as we go from phosphorus to argon, those are going to have low conductivity for the reasons that I've discussed previously with molecular covalent bonding structures. They don't have delocalized electrons and they don't have a continuous network of bonds at all. So they have very low conductivity. So then we can consider the electronegativity. Sodium 0.9, magnesium 1.3, aluminum 1.6. So those are low. We can say are quite low. And as we get to silicon though, 1.9, this is where things start to get into the metalloid territory, less metallic. So right around this point is where we start to see a big change with the structure and the conductivity. And then above 1.9, as we get to 2.2, 2.6, 3.2, those large electronegativities will not favor metallic bonding at all. And of course, argon has no electronegativity. Electronegativity is defined by how much an atom pulls a pair of electrons in a covalent bond. We can't define it for argon. It doesn't really form covalent bonds. So you can see this kind of spectrum or this continuum of where metallic bonding is, which things have the most metallic properties, where it kind of shifts around 1.9 electronegativity with silicon and the metalloids. And this will generally hold true for most of the periods in the periodic table. Okay, moving on. So metallic bonding, what does it look like? It involves the electrostatic attraction between a crystal lattice of positive cations and a sea of delocalized electrons. Really important to memorize this definition or be able to say it in your own words because it's very often a test question. So in ionic bonding, we had a lattice of cations and anions held together by electrostatic forces. Here we have a lattice that is only positive cations. And you'd think they would repel each other, right? Being positive and positive, but they're held together by the glue, that is the electrons that they release from their valence shells. They release those electrons into kind of a sea or an ocean that exists between the cations and holds them together. But this makes them very flexible, malleable, and good conductors most of the time. So I want to show this little animation of what metallic bonding might look like over time. You've got your lattice of cations that don't really move. They're quite stable in an organized structure. But then you have your delocalized electrons. They're free to move all around. They're not stuck at any one location or stuck to any particular one cation. And I have a note here that there would be many more collisions than I'm actually showing here. It kind of just shows the electrons pass over or through, but really they could collide with each other and collide with the lattice. So this was generated with Claude. I think it's just a generally good representation of the delocalized electrons. Okay, what else can we say? Metallic properties. Due to this bonding type, metals are good electrical conductors. Remember, to conduct electricity, we need a mobile charge carrier. In this case, the electrons are free to move. Good thermal conductors. This one's a bit more difficult to explain, but basically when there's electrons free to move and free to collide, there's a lot more transferring of kinetic energy that is possible. Every time a collision happens, kinetic energy is transferred. So if you have something heating one side of a piece of metal, then the cations and the electrons there pick up that heat through collisions, and then they'll also transfer it extremely quickly through the whole lattice. Ductile. So this is a word you might not have heard before, but it generally means things can be pulled and stretched into thin, wiry shapes without like breaking or cracking. Malleable, you might not have heard this word before either, but this means that they can be shaped and flattened into plates without cracking or breaking as well, generally just reformed and plastic. Lustrous, so they are generally quite shiny and reflective. We're not really going to get into this in chemistry, but you can imagine that what it means is whatever light and photons hits them, they're either able to reflect or absorb and then re-emit in the exact same way that they were hit. So in that case, it reflects back, and what we see is just the exact same light that hit them, like a mirror. Okay, what else can we say? So how about looking at how conductivity would actually work? So when a potential difference is applied, those of you in physics will know what this is after you've studied electronics, but basically it just means we put a field, which is like you can put a positive and a negative plate on each side of your piece of metal. Then we generate an electric field. So in this field, electrons in the metal begin to move towards the positive region. If electrons are picked up by the positive plate, more electrons can be donated by the negative plate. This is what would happen in like a closed circuit with a actual power source, a source of electromotive force it's called, that will push electrons through the circuit. So we can kind of look at what this looks like in my little animation here. So we have our normal metal delocalized electrons, but when we turn on an electric field, all the electrons are attracted to a positive plate. They can then be picked up and put into a circuit, and we could add more electrons from the negative plate. I'm not showing that whole complete circuit here, but you can imagine. Here I'm just showing what happens if you apply the field to a piece of metal. All the electrons flow to one side, the side that is positive. So this makes them really good electrical conductors. We have these mobile charge carriers that can move charge around. Why do metals conduct heat? Well, so the tightly packed cations do not normally move freely, but they can vibrate and occasionally collide with nearby cations or other moving electrons. And heat is related to the kinetic energy of particles in the metal, so what we would need to do to transfer heat is to transfer kinetic energy. So this allows frequent transmission of heat through the material. More collisions due to very mobile electrons means more transfer of kinetic energy through space, through the material. So this also means that hotter metal or higher temperature metal is less conductive. This is a really interesting idea as well. So this might not be immediately obvious, but I'm going to show some animations and graphs that will show why this is the case. So here's a graph. This is electrical resistance. So this is the opposite of conductivity, right? So if something is highly conductive, it has low resistance. If something has high electrical resistance, it has low conductivity. Also a bit of a physics topic, but we're bringing it in here to chemistry as well. So this graph shows as we increase the temperature, the resistance increases, therefore the conductivity decreases. So if you want very good conductive metal, it needs to be kept cool. This is also probably why your electronics and things don't work as well when they start overheating. You can't transfer electricity as well. So you can see this is a line. It will have a slope that you could calculate, and it has linear properties. So if you would double the temperature, you would double the resistance. If you would half the temperature, you'd half the resistance. And the same thing goes for resistance. If you double it and you consider what temperature change caused that, it must have been a doubling in the temperature. So for most metals, the relationship between electrical resistance and temperature is linear over temperatures near the standard ambient temperature. So around room temperature, this graph I'm showing is like from 0 to 100, so that's still not too far away in the whole grand scale of temperatures. Generally, most metals, I think, would follow this linear resistance curve. So how can we explain this? Well, higher average kinetic energy in the metal means that you have more drastic and frequent vibrations, not only of the electrons, but of the cation lattice as well. Even though it's solid crystal that's locked in place, those cations can still vibrate, of course. So, as you increase the kinetic energy, you increase the vibration, therefore sort of the area through which the cations can exist in a certain time frame. The area and the volume. I have a two-dimensional animation here, but you have to imagine this is happening in 3 dimensions as well. So this increases the collisions with electrons that are moving nearby. High electrical conductivity would mean a smooth path with few collisions. So that's what I'm going to show at the beginning of this animation. A cold metal where the lattice is vibrating just very slightly and all the electrons can basically move in a straight line when the electric field is applied and go to the right. Let's see that. So the electrons basically have a nice path through. You can see the lattice is vibrating a little bit, and every once in a while there's a collision that would transfer kinetic energy. But overall, this would be a great conductor. The electrons have a clear path from left to right. But what happens if we increase the temperature? Now you can see the lattice vibrating much more. It's covering a larger area and volume in a smaller time. And that means the chance for collision with all the moving electrons increases. And you can see the collision counter I have in the bottom left. The rate at which the collisions happen has certainly increased. What if we go max temperature? Now the lattice is moving around. You can see that the chance that an electron goes from left to right without hitting anything is pretty much zero now. The chance that it hits 1 or 2 or 3 cations on the way is very high. And you can see it's still always attracted to the right side. You can imagine there's a positive plate there, but it'll be blocked every time there's a collision that will slow it down. That's electrical resistance. Okay, so keep that in mind. What else can we say? You guys might have heard of superconductors. This is also a thing that exists. So again, I have a graph of resistance versus temperature here. I have this same straight line with a slope that I've showed on a previous slide. But then we have a superconductor, superconducting metal. It follows the same slope, it's at a slightly different position, but a special thing happens at what's called the critical temperature, TC labeled here. Okay, so if we decrease the temperature enough, could we decrease electrical resistance to 0? It's a great question. Yes, in fact, many metals and some other materials demonstrate this property of superconductivity. So the temperature that a metal has 0 resistance is called its critical temperature, T subscript C. I think not all metals do this, but some, once they reach a certain very low temperature, this one tends to happen at 10 Kelvin, it looks like. We have essentially 0 resistance and almost unlimited conductivity. I guess maybe it happens near the speed of light these electrons could travel. But yeah, this you could imagine would be very useful for trying to send signals or data or build computers or electronics. The problem is keeping anything at 10 Kelvin or below requires a lot of energy, so it ends up being not worth it most of the time for most of the devices that we use. But I think it is certainly used in scientific research or very specialized industrial machines. And you've probably heard some scams recently saying, or people saying that they have built or created room temperature superconductors. That would be really amazing, but I don't think it's really quite worked yet. Anyway, just a few notes about superconductors. I've never really seen questions about this on the exam, so it's just more of a curiosity. Okay, what else? Malleability and ductility. How can we explain this? It's not that easy, but basically it comes down to the fact that we can compare metallic bonding crystal lattices to covalent networks, right? Covalent networks share electrons at very specific locations between specific atomic nuclei. Therefore, there's no flexibility there. But with metallic lattices, the cations are sort of glued together with the delocalized sea of electrons. But if you apply a force, it ends up being flexible or malleable. So what can we say about this? The lattice of cations in metals is not locked in place by rigid bonding, such as that of ionic or covalent networks. Layers of cations can slide within a metal while maintaining their electrostatic interaction with the mobile sea of electrons. Okay, they can still be having the same electrostatic forces with electrons around them. The electrons are constantly moving and rearranging. So if they change position, it actually doesn't cause any breaks or cracks. A force is still required to do this, and the force that is required depends on the metal and the strength of its metallic bonding how much those cations are attracted to those electrons. So I have a little animation here. What happens if we apply a force to the top of this metal? We can just slide layers of cations past each other. So the ones at the top, it looks like, are moving the most distance, and the ones at the bottom are not. So there's going to be some different angles going on here between the cations versus, those at the bottom versus those at the top. But this is something that can happen in metals for sure, and we could even have like actual cutting of these lines, these little thin lines I have between, and they can reform. It's flexible due to the flexible nature of the electron sea, the delocalized electron, mobile sea of electrons. Okay, so they tend not to break or crack or flake or powder as ionic or covalent compounds would do. Metals are good electrical conductors due to free delocalized electrons. This is a summary. Metals are good thermal conductors due to frequent collisions between cations and electrons, which transfer kinetic energy all throughout the metal. Metals can be deformed without breaking chemical bonds. That's an important point. We are overcoming some electrostatic forces to rearrange, but overall the bonds are kept intact, and there's no real structural failure or huge cracks or deformities that happen. Okay, state the properties of metals that would make them good for the following products. 1, pots and pans. What are some reasons for that? So those would be used for cooking. So we want those to be malleable for sure, so that we can make them into the shapes of pots and pans that we want. We would want those to be good heat conductors. So that we can transfer from our stove and then spread it evenly into our food or water, whatever we're trying to do. And I would also say inert. We don't really want our metal to react and then contaminate our food, right? So we have to be kind of careful with the metal that we choose, but we'll generally choose stainless steel, copper, titanium, I don't know, chrome, these kind of things that are inert enough that we don't end up eating too much of them in our food. Electrical wires, maybe you can think of some reasons for that. These need to be ductile, pulled into thin shapes without really cracking or breaking. They need to be good electrical conductors for sure. I think those are the main points. Radiator, this is an interesting one. We want that to be malleable to make certain shapes. You can think of maybe like a car radiator or something. It's trying to remove heat from the engine. What else? We would want that to be good heat conductor to pull heat away from the engine. And there's one more thing I'll say here, which is maybe something new I haven't mentioned yet, but we generally want a material with low heat capacity, I think. This is something you'll learn about in the energy and enthalpy heat transfer section of the course. But heat capacity is something that tells you how much energy the material can store as heat. So something like water can store a lot of energy as heat. So it takes so much energy to boil water or heat it up. But metals are generally the opposite. Putting in a little bit of energy will increase a metal's temperature very highly, much more than if you would put the same amount of energy into something like water. So metals get hot really quickly. They can't hold actually much energy. And then those of you in physics might know that there is an equation that looks like this. Power radiated equals the Boltzmann constant sigma times temperature to the power of 4. So hotter things radiate much more heat. T to the power of 4, that's like much more than any other equations that we've seen. It's proportional to T to the power of 4. So if metals can get a lot hotter with less energy, they're also going to radiate and spread out that energy to the atmosphere or whatever's nearby much more quickly. That's a great property for a radiator, obviously, where we're trying to cool things down and get heat away. All right, artificial limb. What can we say about this? I think we want that to be malleable to get correct shapes for like bones or joints. We want that to be inert. We don't want that to be reacting with things in our body. So we'll choose special metals that have that property. And I don't think we care too much whether these are electrically conductive or heat conductive, but yeah, malleable and inert. Outer body of a car. We want that to be malleable to make cool and aerodynamic shapes. Interestingly, we do want that to be a good electrical conductor. For 2 reasons, I think. I think when the car builds up static electricity from driving over roads all day, we don't want that charge to be stuck anywhere. So you might not have known, but black tires are also good electrical conductors, or fair electrical conductors. So this way, electrical charge doesn't build up and it gets, put back into the ground if it's ever built up anywhere on the car, which is great, so that when you go to fill up your car with gas, you don't generate any sparks and explode your car. Also, if lightning were to strike your car, you don't want that charge to be held in the car and contribute to any heating or anything like that. So we want that to conduct straight through the car and through the tires into the ground and save everybody in the car. Kind of a random thing that we want, but it is true. Violin string. Well, also we want the outer part of a car to be inert so that it doesn't corrode or rust as much as possible and last for a long time. Okay, violin string, we want that to be ductile so that we can pull it into a wire-like shape and then build the violin. I don't think many other properties really matter for violin strings. I guess inert is important. We're touching them a lot with oils and things and water, so we hope that they don't degrade too much over time. Okay. Hopefully you can read most of my writing on this slide, but I think these are the main reasons why we would choose metals for these materials. Okay, let's move on. So we will just go through 2.3.2 as well quite quickly. This is to do with the strength of metallic bonds. How do we find out which are stronger or not, or predict? So metallic bonding, delocalized electrons are not localized to any particular nucleus. They are mobile and free to move through the entire crystal lattice, forming an indistinguishable sea of electrons. The strength of metallic bonding depends mainly on 3 things. First, the number of valence electrons which can become delocalized. So you have to look at the valence electrons. Generally, only the valence electrons, if any electrons, will be delocalized. So things like sodium can delocalize 1 per nucleus. Things like magnesium can delocalize 2. Things like aluminum can delocalize 3. So the more that you have, the stronger your metallic bonding can be. Next, the charge of the metal ion centers. So once the electron leaves and joins the C, you're going to have cations with certain charges. Sodium +1, magnesium +2, aluminum +3. So generally, this goes together with the first point, right? If aluminum has 3 valence electrons to lose, it will have +3 charge. Therefore, when one of these increases, the other one will as well. But next, the ionic radius of the metallic cations. This is something slightly different. But as you get larger radii, larger cations, the electrostatic forces are not as strong. The electrons can't get as close to the center point of that charge. Things cannot get as close together. You guys might remember I've introduced a proportionality here, which is that electrostatic force is proportional to 1 over r squared. So as you get larger radius, the electrons and the center of the nucleus have to get farther apart, and therefore the force decreases. So if the force decreases, the metallic bonding strength and the lattice strength, those kind of things also decrease. Okay. So I have some real data here. Potassium, K, and calcium. Melting points are hugely different between these two metals. These are, I think, going left to right across the periodic table. So first we have potassium. It has only 1 electron. It will create a +1 cation. But calcium can release 2 valence electrons and become a +2 cation. So those two things make its bonding, its therefore melting point, much higher, much stronger bonding in calcium. And then if we look at maybe going down a group of the periodic table, lithium to sodium to potassium to rubidium to cesium, here we're mainly looking at the ionic radius. So we go from 76, then a few jumps up to 167. But lithium has the highest melting point at 180.5 degrees C. Then the trend is it will decrease and decrease and decrease as the radius gets larger. Again, this is due to electrostatic force being proportional to 1 over r squared. R is the distance between the charges, so between the electron and the center of the cation here. That's increasing, therefore the force is decreasing fairly quickly. All right. What else can we say? So moving left to right across the periodic table, metallic bonding, when and if it occurs, increases in strength. Radius will be going down as you go left to right. So the main reasons are there's greater charge on the cations as well. There's more electrons in the delocalized C as well, and then the radius. So decrease in ionic radius, increase in electrostatic force. So everything kind of works together to make metallic bonding stronger. But then if it gets too strong, it ceases to be metallic bonding. Once the electrons get locked in place due to really strong forces, they're going to become covalent networks and covalent molecules. Okay, some practice. Which list orders metals in order of increasing boiling point? Provide reasoning. So boiling point, same thing as melting point, same thing as intermolecular forces and bonding strength. So we have beryllium, calcium, strontium, and barium. So I believe these are just group 2 of the periodic table. So I think it just goes like this: beryllium, calcium, strontium, barium. So as you go down here, radius will be increasing. Radius is really the only difference between these. They're all going to release 2 valence electrons, being in group 2, and they're going to have cation charges of 2+ as they lose those 2 electrons. So if radius defines this, beryllium has the smallest radius. Smallest radius means strongest bonding. So it's either going to be C or D. And then which is the lowest? It's going to be barium with the largest radius at the bottom. Okay, then number 2, which of the following explains why aluminum has a higher melting point than magnesium? So again, if we look, I think this is period 3, we're going to have magnesium somewhere on the left side here, and then aluminum much further to the right. Really, I don't think there's anything in between these except for the transition metals. So what are the reasons? Aluminum contains more delocalized electrons per ion. Is that true? Yes. Aluminum can release 3 electrons, being in group 13, whereas magnesium in group 2 could only release 2. The ionic radius of aluminum 3+ is smaller than that of Mg2+. That is also true. I don't know if I've really discussed this too much in my lessons, but going left to right across the periodic table, radiuses will decrease. You have higher nuclear charge pulling in electrons more strongly. So smaller radius there. That explains stronger bonding and higher melting point. Then third, the charge of an Al ion is greater than that of an Mg ion. This is also true. Al will become Al3+, just like in part 2 of this, and Mg will only become 2+. So all 3 of these would be true and reasons why aluminum's melting point is higher. Okay, I think that's all I have for today. So next time, we'll skip through the HL metallic bonding section and go to structural properties and the triangle diagram to compare between metallic, covalent, and ionic bonding. Thanks for listening. Hope you learned something. See you next time. Bye-bye.